Good morning, everyone. Thanks for coming to the QFT in Physical Mathematics seminar. Today we've got Luuk Stehouwer from Dalhousie University, and he's going to talk about the spin statistics theorem for TQ.
Thanks for introducing me. Thanks for having me here. I really enjoyed CMSA. I've never been here before. So I will talk about the spin statistics theorem, famous theorem for physical theorem for quantum field theories. And I will talk about them in the context of functorial quantum field theories, particularly topological quantum field theories. This is based on some paper, which is by now published in Communications, and it's based on my PhD thesis. Okay, so here's there you go. I was shocked for a second. It works. Okay, here's an outline of what I'm going to talk about. So first, I will recall what spin and statistics are about, and sort of mathematically. Like spin is something about the spin group. Statistics is something about like exchange particles, and how do you describe that for functorial field theories? Then the spin statistics theorem says something about unitary quantum field theory. So how do you say what a unitary TFT is? There are several approaches to that, but I will follow approach using Dagger categories. In particular, I will be, I will make a few digressions then to explain a construction of Dagger categories motivated by work of Dan and Mike, using Z2 actions on categories and Hermitian pairings, just like Hilbert spaces they have Hermitian pairings similar to that. And then I'll make a comment in part 3 of that about the relationship between what I call unitary and what Dan calls reflection positive TQFTs. They're just the same, but it's just a different way to describe them. And then I will sketch how to prove the spin statistics theorem. So first of all, I want to sort of highlight what are the most important aspects of sort of the categorical aspects that we need for the proof. This is something, so there's this notion called Dagger compact categories, which is well established in like quantum information theory, and I need a slight modification of that to the fermionic case. I coin it fermionically, Dagger compact categories, and I will then outline the proof, which is slightly different than the proof I give in the paper just for fun. And then depending on how much time I have, I will go through some extra topics, some higher spin statistics, like more excited types of spin statistics theorems one could prove, and this sort of work in progress on what is a higher unitary TQFT. Okay. That was a long time I spent on explaining the outline, so let's get into the actual stuff. So I'll start with spin and statistics. So first, statistics. Statistics physically is you have bosons, you have fermions. Bosons commute with each other. Fermions, they anti-commute with each other. How do we encode these in state spaces? State spaces are vector spaces, maybe Hilbert spaces. And they are graded by -1 to the f, sort of -1 to the number of fermions. This notation sort of refers to the case where you second quantize a free system, for example. Like if you would imagine having one particle Hilbert space. Can people see this? It's very small. I should write very large. So if you have a one particle Hilbert space, then you usually look at the Fock space. It's the second quantized thing. And here, you have the things that have I particles, and the grading of this is like the grading of this grading operator acts by -1 to the I. So I is sort of the number of one particle states that you have there. Okay, so that's how this notation comes about. So yeah, conclusion is state spaces are super vector spaces or Z2 graded vector spaces. And more mathematically, so we're going to need some more categorical notions because we will do TQFT. So then we need to understand what this means categorically. So there's some vectors, some category of super vector spaces in which the morphisms are the grading preserving maps. And very important will be that this is a symmetric monoidal category. And the symmetry sort of encodes this notion that fermions anti-commute. Like you have this grading, which grading the category of super vector spaces where you get a sign. So that's maybe not in the first part, but the sign is there only if both things are odd in the grading. So if both things are fermions. And there's still a symmetric braiding that you can use. Okay, so this is an ingredient for how to define statistics in TFTs. Also, a brief review on spin. I hope this is sort of all familiar for everyone, but just to be sure. So the spin group is most familiar in the case that the dimension is 3, because you live in 3+1 dimensions. And spin 3 is like, you could see it as SU2. And there's this very important classification of the irreducible representations in terms of non-negative half integers that we call spins. The sort of crucial thing is that if you have an irreducible representation, so if you have a particle that's supposed to live in an irreducible representation of some little group of the Lorentz group, which is, well, okay, some fermionic version of that, which is the spin group in this case. And so this particle is necessarily in one of these irreducible representations, which corresponds to one of the spins. And the spin is integer if and only if it's actually an SO and a representation of SOD. For an arbitrary dimension, it's a little more complicated. Like you don't have this classification of theorems, but still you can talk about this. You can still talk about whether you have, I don't know how to say whether you have integer spin or whether you have a specific spin, but I know how to say whether you're a half integer spin or integer spin, because you still have this element, which I sort of suggestively call -1 to the 2s, because of the last bullet point. If I have an irreducible representation of an arbitrary spin group, I can act with this element in the kernel. So you have this double cover to SOD. And if I act with this element in the kernel, then that's a central group element. So since it's central, it has to be acting, and it's order 2, so it has to act. There's only 2 options. It has to act by +1 or -1. So I will say that an irrep is sort of half integer spin. Okay, so here I say for the vector, it's necessarily, if it's an irrep, it's for the whole vector space. So something has half integer spin if it acts by -1, and that's exactly the case where sort of the representation doesn't descend to SOD. So this seems to be then a well-motivated definition in general. So we have this element -1 to the 2s, and then we had this element -1 to the f. And we sort of, the spin statistics theorem says something that these two should be equal, like something is a fermion if and only have half integer spin, and something is a boson if and only has, wait, I'm saying that correctly? Yeah, exactly. Bosonic statistics corresponds to spin integer. Fermionic statistics corresponds to spin half integer. And you can just very briefly formulate this in terms of an equation right now, just that these two signs are always equal acting on state spaces. And now this theorem should hold for a unitary quantum field theory. So whenever we have an axiomatic framework of quantum field theory, like TFTs, we should probably try and prove something like this if we know what unitary is. So what is unitary for TFT? What do these signs mean for TFTs? So for that brief reminder of what TFTs are, given my audience, I think I maybe didn't really need much of this slide, but okay, I did it anyway. So if you have a state perspective quantum field theory, sort of a more Schrodinger perspective, not from observable perspective, then a d-dimensional quantum field theory should assign to a d-1 dimensional manifold you might call space, a vector space of states, or maybe Hilbert space, but we'll get to that later. And if you have a manifold with boundary space-time between these two manifolds, it's called a Bourdism, has a formal mathematical definition. Then you get a linear map between these two state spaces, which you should think of as time evolution. Like if my space-time would just be like a cylinder of like t or something like that, it would probably give me something like e to the -it Hamiltonian or something of that type. But since I'm going to do TFTs, this will actually always be the identity because the Hamiltonian needs to be 0. Okay, and then this should probably satisfy a couple of axioms, like gluing axioms. And you know that the sort of famous thing of stacking things, that if you take a disjoint union of two manifolds, disjoint union of two systems should correspond to the tensor product state spaces. That's called superposition. Okay, so I could now write down the definition of the TFT, but instead I'm interested in this fermions and spinors situation. So now we need to sort of go back to the previous slides and think, okay, how do we apply then what we learned to this situation? Okay, state spaces should be supervector spaces. Okay, great. And on the geometric side, we need to be able to define things that have to do with spin, like spinors and things like that. So we should probably put some spin structures in there. And then I get to this definition. I'm not sure if the terminology is reasonable, but just for this talk, I will call these things fermionic TFTs, which are symmetric monoidal functors from the logarithm category with spin structures. Like usually people do orientations, now we need spin structures, and they go to supervector spaces. Okay, and this is a symmetric functor, so it really remembers this sort of causal sign kind of thing, that if I exchange two order of two vector spaces, then I will get the sign. Maybe a brief remark for the rest of the talk is that I'm just now working with spin structures, but if people like more general sort of symmetry groups, if that means anything to you, so sort of maybe that's one thing to say, sort of until where it's visible. I can even write there. Okay, so anyway, like I sort of assume that the internal symmetry group here is something like there's only a fermion parity, but that's just sort of for exposition reasons. If I would be able to do this for an arbitrary symmetry group, including time reversal, you could even do a bosonic group, and surprisingly, the talk would still be interesting because the spin statistics theorem would say something like, in a bosonic theory, even when you take the target to have things graded, they necessarily need to be even, sort of a bosonic lame version of a bosonic spin statistics theorem. But from now on, I will just pretend I didn't say this, and I just only work with the spin theories, but that's, there's a generalization. Okay. So how do we formulate the statement that spin and statistics are equal for TFTs? Okay, so first of all, we have this operation -1 to the 2s. How do we act with -1 to the 2s on state spaces? Well, -1 to the 2s, this special central element in this kernel 2SOD, it always gives an involution of a spin principal bundle because it's a central element, it scores to 1. And if you have an automorphism of a spin manifold, whatever you want to call that, something like a spin diffeomorphism or something like that, this always induces a mapping cylinder construction. So there's always a Bourdism, which maybe looks kind of trivial, like it's just a cylinder, but actually the way that it acts is via this mapping cylinder, via the diffeomorphism. So in particular, if you apply this to this -1 to 2s thing, that means that every time slice of sort of every object, that's what I call time slice, so an object of and the d-1 dimensional closed spin manifold has an involution given by this -1 to 2s operation. Okay, and then if we're given this fermionic TFT, then we can apply the TFT to it, and we get an involution of every state space that you might reasonably call the involution that determines which things have integer spin and which things have half integer spin. And then there's this other grading operator, which we call -1 to the f, and that's just the super grading, which acts by 1 on the even part and -1 on the odd part. Okay, so now we can say that these things should probably be equal. So just to sort of distinguish the terminology a little bit, people usually talk about the spin statistics theorem, and it's sort of a little bit, I don't know. So I want to introduce the terminology here. I don't know if it's good, saying that a TFT, which is a quantum field theory, which is not necessarily unitary, has a spin statistics connection if being half integer spin is the same as being a fermion, and then refer to the theorem, which says that every unitary TFT has such a thing as the spin statistics theorem. So it could happen in theory, I mean, it does happen, that there's a quantum field theory which is not unitary, but it still satisfies, it still has a connection between spin and statistics. So in this way, we can separate these kind of things. Okay, so now we have formulated it in a rather abstract way. So apparently a TFT has a spin statistics connection if it's BZ2 equivariant. So this turns out to be convenient formulation. So BZ2 here is the 2 group, which is the sort of loop, the delooping of Z mod 2. So the point is here that for example, super vector spaces, it doesn't have a Z2 action by -1 to the 2f. That would be that you send every vector space to some other vector space. That would be an action. But now we send a vector space to an automorphism, to an involution. That's called a BZ2 action. It's a natural thing. It's a natural automorphism. Every object, natural involution. And the statement that I just made, that sort of a Z of the spin flip is -1 to the 2f, -1 to the f is exactly the statement that this functor is BZ2 equivariant. So we can formulate it in terms of equivariance. Okay.
Am I correct to understand that you are, at this point, you are talking about non-extended?
Oh yeah, I should have mentioned that. This whole talk is basically about non-extended TFTs. Maybe all the way at the end in the outlook, I will say some things about extended TFTs. And like, because there's so many interesting open questions right there. But this talk is just about the very simple situation, the non-extended TFTs. That's right. But this definition.
So if this definition, so after this definition, then hazard spin static state connection is conditional only.
Exactly. Yeah. I think.
Seems that if you correctly formulate in the way that it is becoming the structure, then
right.
that definition also makes sense.
Yeah, exactly. This is like another motivation that I didn't say why I formulate like this, because if you say it has a connection, then it sounds like it could be data. So I didn't want to say that, but now that you say that, that's right. So if you're once extended or even more extended, then BZ2 equivariance is data. And then, yeah, I mean, like you can imagine that by that point, so for example, if you're once extended, I can write here, right? So you're once extended, then you can imagine we have a dimension 2 manifold, and this gets mapped maybe to some category, or I don't know what the target is. This is some target in some category. And the thing is that this has an automorphism exactly. And then you need, and then automorphisms also have morphisms, so it's 2s. And then exactly the equivariance would say that there's some sort of datum of the form C of -1 to the 2s. It's no longer equal, but it's now equivalent as sort of it's naturally isomorphic to. So it's not involution on this. If this is probably like a super category or something like that. But yeah, that's right. As you go further, spin statistics, satisfying the spin statistics, like having a spin statistics connection is actually a data.
You're expecting that theorem is forced to.
Yeah, I think so. But I have no clue. I haven't tried to do that. But
with what target? Like even as a category.
Oh yeah, exactly. With what target? Yeah. Yeah, I don't know. Yeah. Well, in this setting, something like.
Similar to this on for formulating the higher categorical unitarity.
Yeah, that's a related kind of question, which I will maybe get to all the way at the end. But definitely, like maybe that's a good remark to make in this context. Like already in a non-extended situation, the spin statistics theorem definitely doesn't hold for arbitrary targets. It strongly relies on the target of super Hilbert spaces. And I don't have a good intuition at the moment what exactly is special about super Hilbert spaces that makes it work. It's just very clear that it doesn't work for arbitrary targets. So something similar must hold once you go further down. I mean, I do have the feeling that it would work for something like 2 Hilbert spaces for once extended, but I haven't really thought about it, so I don't want to make a precise statement.
Your target is super Hilbert spaces or super vector spaces?
Oh, sorry, what am I saying? Yeah, well, the problem is that I didn't define yet what a unitary TFT is, but once you say, I mean, if we want to talk about whether the spin statistics theorem holds for a given for a given target, then we better have a definition of what a unitary TQFT is. So I have to, and for that, I need to choose my target to accommodate for positivity and things like that. So I will need the target to have this structure of, for example, super Hilbert spaces to remember what kind of positivity I require. I will get to this, maybe then it will become more clear. So it's a little bit preliminary. Yeah, it's probably better. Yeah, let's get back to it again once I have said what I mean by unitary TQFT. So, okay, how to define this? And my favorite approach is using Dagger categories. So this was already, I think, in the original paper of Attia, he already sort of sketched the definition of a unitary TQFT using this approach. One thing that's maybe missing from a lot of from TQFT, if you're a physicist, you maybe wonder, oh, why are state spaces just vector space and not Hilbert spaces? And that's because unitarity is not directly implemented. In a unitary TQFT, in a unitary quantum field theory, vector spaces should be Hilbert spaces. In particular, they should really have positive definite inner products. And what is one extra categorical structure? Like, we have to identify categorical structure if we want to make definitions in the TQFT setting. One structure that they have is that they are a Dagger category. I wrote out what is the definition of a Dagger category very briefly. A Dagger category is a contravariant functor on a category which is an involution. It's a strict involution. It squares to the identity on the nose. There's no natural isomorphism. And it's also the identity on objects. So in this case of Hilbert spaces, this Dagger operation is given by sending a Hilbert space to itself and sending a linear map to its adjoint operation. Yeah, so this symbol is pronounced Dagger, just like physics. Okay, so already Attia formulated, like, he focused on the oriented case, but the observation that he used is sort of that one very natural thing to do, at least mathematically, is that you can reverse the direction of forwardism and simultaneously orientation reverse. And this defines Dagger structure on forwardism in the at least oriented case. So this is the idea. And then you can define a unitary TQFT as something which sends this sort of daggering operation to, maybe quotes here, this daggering operation to the daggering operation of Hilbert spaces. And then you get some restriction on what kind of functors you allow. So yeah, the bosonic definition, the unitary TQFT would be a symmetric noidal Dagger functor. There's maybe a slight star here that I didn't explain what a symmetric monoidal Dagger category is. Like, you need to, it's more than just a Dagger category that's symmetric. Okay. The thing is that we want to do now is we want to, we don't want to just do oriented boardisms, we want to do spin boardisms, and we want to do not Hilbert space, but super Hilbert spaces. Yeah, oh yeah, so probably people know what board SO means, oriented boardisms here. Okay, so the question is, if we want to use this definition, is how do we build a Dagger structure on spin boardisms? And the answer is, well, actually similarly to how we define a Dagger structure on Hilbert spaces. Hilbert spaces, like vector spaces, have a complex conjugation action, and you can define Hermitian pairings with respect to that and use it to define the Dagger. That goes as follows. I will just do it for super Hilbert spaces so that we immediately have that out of the way. So there's a Z2 action on super vector spaces, which is given by complex conjugations. It's not a BZ2 action. So maybe I should also write something about that. This is probably a little bit of a dense slide otherwise. So, of course, I lost my chalk. So there's a notion of a complex conjugate vector space, which is the same vector space with complex conjugate scalar multiplication. And this is not equal, but there's an isomorphism that satisfies some conditions, and it's called an action on a category. Okay, and now how do you define categorically what Hermitian pairings are? Well, they're sort of non-degenerate pairings between a vector space and its complex conjugate. That's a sesquilinear pairing. Here by non-degenerate, I mean that one of them realizes themselves as the dual to the other. That's too strong to require if you're interested in infinite dimensional things. But we do finite dimensions because that will be automatic for TFTs anyway, so this is fine. And then there's some diagram which I wrote down which commutes, and it's basically sort of the analog of the usual Hermitian condition that you want to require this bar. The thing is that we're now in superworld, so there will be a sign here. But this diagram is just a limitation of this usual Hermitian rule, the symmetry rule. And then for super Hilbert spaces, we need to require additionally a positivity condition. So the conclusion of this slide is sort of a little bit of an abstract situation that if you have a category with Z2 action and duals, you can talk about Hermitian forms on them, and then you can restrict some of them. And it turns out to be the case that from that information you can build a Dagger category already. So that's this slide. So if you have a category with a Z2 action, symmetric monoidal, then you can build what I call the Hermitian completion. So that's like Hermitian vector spaces version of the category. And the objects are pairs of an object and a non-degenerate pairing on it. And confusingly, the morphisms are just all morphisms in C. But that's, if you think about the example of Hilbert space, it's not so confusing. Because also in Hilbert spaces, the morphisms are just all linear maps. The thing is that you remember this extra Dagger structure on it. And this Dagger structure, you can, for example, build as follows. So since in this Hermitian completion, every object comes with a canonical dual, namely the complex conjugate, it has a dual functor, and this dual functor has the strange property that if you compose this dual functor with the Z2 action, it is the identity, it's the identity on objects. So this becomes a Dagger category. You can write down what this means, and it turns out that if you work out what this Dagger does, it just does the same thing as it does on Hilbert spaces. It does the usual formula. Okay, and now more generally, like now we have this big category. You can also look at subcategories of this. Like for example, if you would restrict the non-degenerate pairings on vector spaces to the Hilbert space pairings, then you get if we want to look at CP, CP, sort of the full subcategory generated by those positive pairings. Okay, so that's how you can build it.
Do you want to write PP?
Sorry, what?
I'm confused. So you already require the non-degeneracy.
I require non-degeneracy, yes, for H.
In the definition and in the bottom item you.
Oh, sorry, is this? Yeah, maybe I don't remember how I define Hermitian pairings. You're saying Hermitian pairings are all automatically non-degenerate or not? Sorry, I probably don't remember.
Zeros.
Okay, yeah, I forgot how I defined it on the last slide. Oh, I didn't define it. That's a good solution. Okay. Yeah, so I guess that Hermitian pairings are maybe ones that satisfy the symmetry condition, and then they need to be non-degenerate, so realize X is the dual X bar. Yes. Okay, so this is a trick that you can use to, you can just read Dan's paper with Mike and just copy his definition of Z2 action on the boardism category. You will get a definition of the spin Dagger boardism category. So here's a brief review of what happened there. The idea is that orientation reversal actually comes up in this picture. So there's an orientation reversal Z2 action on the spin boardism category. And I just outline it here. So if you have a spin principal bundle, you have the pin, it sits inside the pin group, spin sits inside the pin group. Pin group is sort of twice as large. So I can make an associated pin bundle. which has two parts. And one part exactly looks like the original bundle, but there's some other part, and that other part I call P bar. That's my model for the orientation reversal. You can imagine what would have happened for the case where instead of spin I would have SO, and instead of pin I would have O, and then this is not this very strange definition of orientation reversal. And you can make this work with boundaries and with spin structures and everything. So this defines a C2 action. Okay. And then you can define Hermitian parents for this structure, for this D2 action. And here's one construction. And just for fun, I do a different construction from the one that's in Dan's paper, but it's the same as, it's equivalent to what Dan does. It's the same map. So, okay, we have an object of the spin Bordism category, and we want to make it isomorphic to its orientation reversal dual. So we take an n-1 dimensional closed spin n manifold, and I use a model of that for which I have a spin n structure on the tangent bundle direct sum with the real number, with the trivial bundle, because that's sort of what happens in the Bordism category. Like on boundaries, you have a normal vector anyway. Okay, so spin structure for me is spin n bundle, and then it's a spin structure on the tangent bundle. So I have a vector bundle isomorphism between the associated bundle to the standard vector representation of spin n and this thing I have a spin structure on. Okay, and if I have this beta, then I can evaluate beta on different points of the principal bundle, and in this way, I can get vector space isomorphisms. And if I have a metric, which I'm assuming I have here, because spin n sort of includes a metric for me, it's actually not important, because like in TFTs, it doesn't matter whether you have a metric or not. So it's sort of, I don't know, the space of metrics is contractible, but it turns out to be used here. Okay, so an isomorphism of vector spaces with the form induces an isomorphism of pin groups, and this I can use to define an isomorphism between P and P bar. So why is it as an isomorphism between P and P bars? Because I act with an element of pin which is not in spin. So this should have been a plus here. So I have this specific element of pin, which is generated by sort of this vector right here. So the last basis vector, like I don't have a basis for a tangent bundle, but I can do that. And then I can act with that on P. Excuse me. Okay. So I actually now have for every object of the Bordism category a preferred pairing on it. And I'm going to use exactly those pairings on the Bordism category to make it into a Dagger category. And this is basically the same as what Dan and Mike do in their paper, except I formulated it in a different way. So yeah, a unitary TFT is then a symmetric modal Dagger functor from this specific spin Bordism Dagger category to super Hilbert spaces, Dagger category super Hilbert spaces. And another definition that I could make is the same definition, but I don't require positivity of the Hermitian forms. So it's a Dagger functor to, well, I wrote it as Herm of S-vect, so the Hermitian completion of S-vect. But if you remember my definitions, what that means is just forms with arbitrary signatures, not necessarily positive. So now I want to just make a brief detour to compare this to Dan Mike's definitions. And I mean, I call these Hermitian and unitary. Dan and Mike call them reflection and reflection positive, which might be better because everything should be thought of as Euclidean signature, but I wanted to give it just a different name so that I can write down this theorem mainly, which is that, so what they do instead is they don't talk about Dagger categories at all, but instead they talk about C2 equivariants. And then they write down a condition for when a Z2 equivariant TFT is positive. And this condition is basically exactly that we take these pairings that I just defined, these elements of P, and we check whether those get mapped by the Z2 equivariant functor to positive pairings, so to super Hilbert space pairings. And this turns out to be the same. There's just both spaces in both cases are equivalent. So somehow this Dagger stuff is very closely related to equivariance. And it's convenient, I think, to formulate it like this. It becomes very clear what the data is and what not. What's conditioned. Okay, maybe I should have paused here so for questions. They're saying. Not, I will go to the proof of spin statistics theorem. Okay, so first I will just I'll sort of take a step back and just do a couple of computations using mapping tori to figure out what could be a good condition that we can prove separately, which is equivalent to the spin statistics connection, and that is this lemma. So okay, if you have a symmetric monoidal category with duals, you have notions of traces. Maybe I should briefly write that down. So just a reminder on traces. So I can, if I have a morphism, I think about morphisms to string diagrams. If I have a morphism from some object to itself, then I can try and make a picture like this using the duals. The problem is that you cannot really close up this picture because sort of on the one hand, you get like the X and X dual, and on the other hand, you get, well, the co-evaluation needs to go in the other direction. So to make this picture, you need to put a grading in. So this picture sort of defines the trace of a morphism in a symmetric monoidal category. You can have more general notions of trace. But these type of traces are always preserved by symmetric monoidal functors, and traces, so the trace in the super vector spaces is the super trace, and the trace in the trace in the Bordism category is basically some sort of mapping torus like construction. I guess slightly more general if your Bordism is not a diffeomorphism, but if it's something like a diffeomorphism, is just the mapping torus associated to that. So now I do some computations with that. So so I'm computing Z of Y cross a periodic circle and cross an antiperiodic circle, and Z of a space cross periodic circle is just the mapping torus of the identity. So that's going to be the same as the super trace in the target. What happened? My screen is not black. Okay, interesting. Okay. Okay. So this is going to be the super trace of the identity, and the super trace of the identity is just the usual trace of the grading operator. Okay, great. Now we can do the same for the antiperiodic circle. The antiperiodic circle is instead the mapping torus of the -1 to the 2s operation. So I can do exactly the same computation and conclude it's a super trace of what the TFT does to -1 to the 2s. So I get that it's the trace of the composition of these two things. And then in this lemma, this is where some stuff comes up about that we're actually, this is actually the only part in the proof where something about super Hilbert spaces comes up, namely this arrow, this arrow here. So that's rather interesting. So the lemma gives a sort of computational check that we have to do for when TFT has a spin statistics connection. Namely, this trace is like awfully close to the thing that we want to be. Sort of, we want this thing to be 1 here. That's essentially sort of what we want for the spin statistics there. But we can so we can do this short computation using that these operators have simultaneous eigenbases to conclude that this is equivalent to the ungraded dimension of the state space being equal to this partition function. Yeah, so they compute because it's basically by definition, right? So every by definition of the morphisms in supervector spaces, everything commutes with -1 to the f, and they're both involutions. So now you can just both diagonalize them, and then you realize that that the trace of their product is equal to the dimension if and only if they have exactly the same eigenvectors. So they must have sort of the maximal, so that their trace is going to be the maximal amount of ones. So everything there's a 1, so that's going to be the dimension of the whole space. Okay, so now we're going to use that as a guiding principle.
Sorry, can I ask? So,
Sure.
You say this part is the special thing about the superhuman. And so I confused. So what kind of generalization you have in mind? What kind of target category you can think of? Well,
I mean, we can. Yeah, that's a good question. Yeah, what kind of target category you can think of? I mean, I'm really, I'm a type of person who is really sort of thinking of these TFTs in terms of like, I think that's the most natural target is vector spaces over the complex numbers and supervector spaces. But some people might think of TFTs differently and have more exotic targets in mind. I'm not very sure. But I mean, one thing, what do I want to say?
For example, the general Dagger category.
How? Sorry?
General Dagger category.
Oh, a general Dagger. Yeah, okay, that's exactly. If you do a general Dagger category, well, you need to have it with a BZ2 action, right? And like already, I think, as I said before, already for just Hermitian vector spaces, it doesn't work. You really need something with the positivity built in. So it's definitely not the case. Maybe the thing that I should have said is that fascinatingly, this will come up in a minute. We don't need much of the Bordism category, actually. Like you can replace the Bordism category by a Dagger category satisfying a sort of small reasonable condition. So somehow that thing is very replaceable, but super Hilbert space is not very replaceable. But yeah, you can definitely not just replace everything with arbitrary Dagger categories. Yeah. Yeah, that's an interesting open question, I think. Like, what is mathematically the reason that it works for super Hilbert spaces? Okay, so the small condition that I just mentioned is what I call fermionic Dagger compactness. So I made some things blue here. The usual definition of Dagger compact is without the blues. So Dagger compact is this notion due to Peter Selinger, who introduced Dagger categories. I'm not sure if the name Dagger compact is a great name. It's just a name. But it says something about, well, I'm soon going to give an equivalent definition. This is a definition in terms of the construction that I gave, in terms of the Hermitian completion construction. But essentially, it means that you can, it's very closely related to the problem here. So here I wrote down the trace, but if you have a Dagger category, there's something else that you can do. Namely, instead of using a co-evaluation and then a flip, I could use the evaluation and then Dagger it. So that's sort of the what this thing answers. So is there a relationship between if you take the evaluation of something, is this related to the co-evaluation? And it is if it doesn't need to be general, but it is if you're Dagger compact. And if you're fermionically Dagger compact, it's related up to the BZ2 action. And this is just a computation that you could do in Hilbert spaces or in super Hilbert spaces, where you figure out that There's several equivalent ways to write it down, where some diagram commutes, or this is equal to that, or it's not equal to that up to a sign. So that's what I call a fermionically Dagger compact category. There's a definition which is only in terms of Dagger categorical information and not in terms of the Hermitian pairings, which might be better. But I decided here to write it in terms of the construction. And then you can prove this lemma that the spin-borism category is fermionically Dagger compact, and that, as I said before, is sort of the only thing that really goes into the proof. And it goes in as follows. So here's sort of this diagram. Diagram 1 is actually, that's what I started saying here. So there's this relationship between evaluation Dagger and co-evaluation. And using that, you can relate two types of traces. So if you have a Dagger category, like a monoidal Dagger category that's not necessarily symmetric, then you also have a different notion of a trace. You have maybe I call it a Dagger trace. I'm not sure if it's in the literature. I think it's in the literature. I've seen it used by Chinese, which is sort of the same picture, but then instead of using the braiding and then the evaluation or co-evaluation, you just take the previous thing and then you Dagger it. I'm being a little bit sloppy with co-evaluation and evaluation, the directions, but it doesn't really matter what you choose. So this is sort of another thing you could do, and you can wonder if these things are the same in a Dagger category, and it is if and only if it's a Dagger compact category. And if it's not a Dagger compact category, then instead they differ by a sign. So for example, in super Hilbert spaces, you have two very natural notions of the trace. You have the notion of trace induced by the symmetric structure. That's the super trace, but then the trace induced by the Dagger structure, that's the ungraded trace. And that's also the reason that this ungraded dimension comes up in this proof. Somehow the Dagger dimension comes up here. And now this proof is the proof of the spin statistics theorem, and it's rather short. You just have to sort of compute, realize that on both sides you have this equation that relates the Dagger to this braiding, and the Dagger evaluation to the braiding, and the co-evaluation, and you just do a short computation. And yeah, the Dagger dimension here comes up on both sides. Yeah, and this proof is, I would say, I should have said this before. So the spin statistics theorem for invertible TFTs was already proven by Dan in his paper. But this proof is basically homotopy equivalent to his proof. I give a different proof, even though it proves more than his proof. And I give a more category theoretic proof in the paper for people who are also excited about categories like me. But this is maybe slightly more geometric and easy to visualize, that somehow the evaluations are just these macaronis, and you can Dagger these macaronis, these elbows, and they don't give the elbows in the other direction. There's just some spinning flips that you have to very, very cautiously keep track of. Okay. Any questions about this?
Sorry, I just confused about the logical way of it. So why does this computation proves the original?
Oh, sorry. Yeah, I was being very fast. So this computation shows that this is equal to that, but then there was just a few slides back, there was this lemma that shows that having a spin statistics connection is equivalent to these two numbers being equal. So I proved that if you have if your Z is unitary, then if you're a Dagger functor, then it has this spin statistics connection. And I mean, I didn't go through the steps of the proof, but it's essentially just realizing that this can be written as these type of pictures, like the mapping torus. Okay, you need to put this -1 to the S in somewhere. And then yeah, you need to use that the dagger is preserved. And then you conclude, yeah, it's a very short proof once you have sort of everything set up.
Does this proof use positivity or just the call it Hermitian? Does it hold for Hermitian?
Oh, does not hold for Hermitian theories, no. Good point, where does it come up? Let's see, yeah, that's actually a very good point. Yeah, I'm sneakily using here that that these evaluations get mapped to each other, but the problem is, which I do very carefully in the paper that I'm writing, but I'm not doing it carefully here, that duals and daggers, they don't go together very well. It's a little bit subtle because like duals are defined up to unique natural isomorphism, but dagger categories are sort of evil. They depend on choices. So one problem that you have with dagger categories, which is very annoying, is that if you have a symmetric monoidal dagger category, then there's not really a canonical dual functor on it, and there can be multiple unitary isomorphism classes of dual functors. But this problem somehow doesn't happen for Hilbert spaces. I didn't want to get too deep into sort of duality. There's a paper of Dave Penny's which he explains like a lot of this.
Can you say where positivity comes into the proof, or give an example of a Hermitian but not positive theory for which this fails?
Yeah, so let's see, how can I best phrase this? I will have to come back to you later. I just cannot answer it directly in front of the camera, I guess. But we can talk about it after. Yes, okay. Anyway, so okay, this is the proof, maybe with some hand waving somewhere. And yeah, so I wanted to get into some possible future directions. So as was already mentioned, like one of the things that I'm interested in is also trying to extend this. And I phrase my talk in such a way that hopefully the following thing is sort of natural. We use Z2 equivariance, we use BZ2 equivariance. Our definition of unitarity used two steps. There was the Z2 equivariance and there was the Z2 positivity, depending on how you think of it. If you think of it in terms of in sort of a Dan style way, that's how you would think of it directly. I did it using dagger categories, but in fact, how I made the dagger categories is just by first doing something equivariant and then putting this positivity conditions in by choosing my set P, my Hermitian pairings in such a way that it would work out. So there's this observation which I learned from Theo, maybe it goes further back. He wrote a paper on spin statistics, in which he realized that these are the two homotopy groups of the O, and he sort of claimed or speculated about the relationship, especially because if you're doing non-extended TFTs, then these are somehow the only two homotopy groups of O that you would be able to see. So maybe there is something going on, and you can talk about O equivariance as well. If you are somehow able to define an O action on boardism categories and an O action on your target category, I think the latter is the most questionable, but that's because I don't know a lot of targets for TFTs, which are 3 categories or 4 categories. And it only becomes interesting from dimension 3 up, dimension 2. As I say, there's, or or at least like if you're once extended, then the sort of next homotopy group is not there yet. So this could be an interesting question for the people who construct these targets, whether they have O actions or not. And then there's, but it turns out that you can often say a lot of things for invertible TFTs because you have this great formalism in which there is a universal target, formulate everything in terms of homotopy theory. And we know how to do homotopy theory. We don't know how to do higher categories. So then you can do these kind of things. And it turns out that this O equivariance does hold for unitary theories. And here unitary theory, by unitarity, I mean the way that Fried and Hopkins formulate unitarity for invertible theories. But I think it was an observation of Lucas that actually, if you stare at it long enough, then their definition is actually also a definition in terms of Z2 equivariance and Z2 positivity. So in the same sense, like there's a sort of some formalism of higher Dagger categories, and what they are doing is they're doing sort of Z2 Dagger categories. It's equivalent to doing Z2 Dagger categories in their paper. So
Yeah,
this is, sorry.
Can I ask how do you define invertible TFT with target ID?
Oh, there's a shift, right? Is that your question? Or I forgot the shift.
The target would be ID means what? So you
Oh.
are maybe defining it as just a functor or a morphism of spectrum.
Yeah.
Not something not the
Yeah, this is related to the discussion that we had before, right? So what I mean, any connective spectrum is in particular a symmetric monoidal category, right? So I can use it as a target, and then by the Galatius, Madsen, Tillman, Weiss theorem, that is actually the same as a spectrum map from the Madsen-Tillman spectrum. But if for some reason I like the infinity n Bordism category more than that spectrum, I could in theory just write it as I have a functor of symmetric monoidal infinity n categories from the Bordism category to some very specific symmetric monoidal infinity n category, namely one that's actually just an infinity zero category, and even more, it's group-like, and it corresponds to a certain spectrum. So that's what I mean. And it's maybe questionable if you would call that a TFT, but it is a functor of infinity n categories, so you could phrase it like that. Yeah, so anyway, the conclusion of this is that this is sort of a theorem of the form Z2 equivariance and Z2 positivity, which I call Z2 Dagger, implies O equivariance. So sort of there's an unexpected amount of, there's more equivariance than you would expect. So this is a perspective which I learned from Theo, that you can see spin statistics theorems as you impose not just equivariance but positivity, and then you get lots of equivariance for free. And this VZ2 equivariance, apparently there's an invertible case, at least much more. It would be very interesting to figure out if this also these type of things hold for extended non-invertible TFTs, if we can make sense of O equivariance and O positivity in interesting targets like the ones that are being constructed by Dan and Theo. Yeah, okay, I already sort of mentioned extended Dagger categories. So there are stronger versions of unitarity, even stronger than the ones using, if you're extended, then you can still talk about Z2 equivariance, and you can still talk about Z2 positivity, but the extra space gives you more opportunities to talk about O equivariance, about O positivity, which sort of give a notion of, it gives a stronger notion of unitarity, potentially, something you could call O unitarity or something. So yeah, by now there's definitions of these kind of things, like together with Cam and other people, we have defined these kind of things. But I just want to bring up this question for people who are listening in the audience. Is there a reason to do so? Like, I don't know, are there any physical reasons? I would like to talk to people who know more about physics, who have some feeling of what to expect for unitary TFTs, because now there's apparently several definitions, stronger and stronger definitions which are the ones that we should use? Should we expect higher versions of spin statistics for them? I think that's an interesting question. Yeah, I'm now also already saying point two in some sense. So on the previous slide, I talked about Z2 positivity implying O equivariance, but there's even a stronger thing, which is O positivity. So is O positivity automatic if you're just Z2 positive? And for which type of targets would this be true? Is it even possible to make targets like that? I think that those type of questions are at least mathematically interesting. I would be curious to figure out whether they are physically relevant or not. Oh, and I wanted to finish with sort of this conjecture right here, which motivates a little bit why I said, so I think I already sort of stated this condition of fermionically Dagger compact as a relatively reasonable, like a small condition, which is maybe mathematically reasonable, but it's naturally, I think, comes up in this higher Dagger framework. I expect that if you are O Dagger, not just O1 Dagger, well, then in particular, you're O equivariant. So as I said before, then you have the Z2 action, you have the BZ2 action, and you have nothing else because your homotopy level is too low. So you have for free at least. So clearly an O Dagger category is a Dagger category with a Z2 action and a unitary BZ2 action. But apparently it's even fermionically Dagger compact is what I think. It might even be equivalent, I'm not so sure. But this sort of naturally comes up in this framework. So that's something that would be cool to work on, I think. Okay, I'm end here. Sorry for going over time.